Hi, we're going to finish chapter 4 today. So the first thing we're going to discuss is carbanion stability. Carbanions, remember, are carbons with a lone pair on them, so they are negatively charged. These compounds are kind of like the opposite of carbocations, which have a plus charge. Well, the carbon having the negative charge is destabilized by alkyl groups. So basically, the tertiary carbanion is the least stable and the methyl one is the most stable. Notice that it's opposite, okay, of free radicals and carbocations. Part of the reason is because the carbon is sp3 hybridized, and that sp3 hybridization keeps the R groups from being in the same plane as the carbon that has the charge, and so you can't have hyperconjugation. Also, the idea of hyperconjugation and induction is they're sending electron density. Well, if you're sending electron density to something negative, it won't want it, so it will repel it, and so that's part of why it is less stable. Carbanions, however, are amazingly great bases. They're very powerful. They're way stronger than hydroxide ion. Okay, they're also excellent nucleophiles. And they will even remove, the bases are so strong that they'll even remove a hydrogen from, or a proton, I should say, from ammonia. So here is an example of a carbanion removing a proton from ammonia to make an alkane and leave NH2 minus. NH2 minus is called an amide. Sodamide is one of the main ones that gets used where the sodium is the counter ion to the negative on the nitrogen. But notice that the alkane, would you even consider the proton in an alkane to be acidic? No, nobody would, right? If you said yes, then you're going to have to come talk to me. So nobody would. And so what happens is that makes the conjugate base way stronger. Okay? So remember that carbanions are excellent bases. Okay, carbenes, the carbon is neutral, but it is also electron deficient because it only has 6 electrons around it. The 2 in each of the bonds to the CBr in this example, and then the 2 that are over all by them lonesome in a hybridized orbital. Well, the hybridization of the carbon in a carbene is sp2. And the pair of electrons are found in an sp2 hybridized orbital. The p orbital is empty. So while carbenes are really kind of odd, maybe, they are highly reactive, and they have their presence in reaction mechanisms has been proven. Okay, remember the p orbital is empty and the lone pair is in an sp2 hybridized orbital. In order to make a carbene, you need a strong base and a carbon with a leaving group on it like a halogen. So here's an example using tribromomethane, and hydroxide ion is a strong enough base to pull off that proton. That gives you a negative charge on the carbon, and then it just says adios bromine and makes the carbene. Okay, and these two steps occur very quickly. All right, so when we talk about more carbene reactions and what they do, we'll go back over the formation of them. Okay, to review, carbocations, the carbon that is a positive charge is sp2 hybridized. Okay, none of these, we're going to say that none of these have resonance at the moment. Okay, so tertiary is the most stable because of hyperconjugation and induction, and methyl is the least stable. Typically, carbocations are considered electrophilic. That means they love electrons. They need electrons. Okay. They also can be considered strong acids in the Lewis sense of acids and bases. Free radicals, the carbon with the free radical on it is sp2 hybridized, like the carbocation. The extra electron is found in a p orbital, And tertiary is more stable than secondary than primary than methyl because of hyperconjugation and induction. Okay, free radicals are electron deficient species and they are also highly reactive. Carbanions, the carbon has a lone pair and a negative charge, and so that makes that carbon sp3 hybridized because there are 4 sites of full electron density, 2 electrons. So the lone pair on the carbanion is found in an sp3 hybridized orbital, and it is destabilized by R groups. So a methyl carbanion is more stable than a tertiary. Okay, these are typically nucleophiles. That means that they're going to donate their electrons, and they're also considered strong bases. The carbines have only 6 electrons around them. The carbon of the carbene is sp2 hybridized. It has a lone pair that is found in an sp2 hybridized orbital, and it has a p orbital that is empty. Carbines do their own thing, let's just say right now, okay? They're looking for electrons and they're going to add to them so that they can have all 4 bonds again and have 8 electrons, okay? So those are the 4 types of intermediates that were introduced in this chapter. I have 2 last things to go over. One is the Hammond postulate. Hammond was a scientist who was an organic chemist. Okay, that's how this came about. He says that related species that are closer in energy are also similar in structure. In other words, on a reaction coordinate diagram, okay, if the transition state is closer in energy to the starting material, then it looks more like the starting material. If it's closer in energy to the products, it looks more like the products. Okay, if you have an endothermic reaction or even an endothermic step, the transition state resembles the product of that step, because remember that the products are higher than the reactants in an endothermic reaction. So here's an endothermic reaction. Okay, so you have a starting material down here on the left and you have a product on the right. The transition state, and let's look at the blue one first, that's the top one. The transition state is closer in energy to the product. Now notice that on the green one it is also, okay? And if you look at the mechanism on the right where they're showing chlorination, which is highly exothermic, you'll notice that the transition state, the hump, is closer to the starting materials, okay? Now, also notice that the difference in activation energy between the 2 possible products you could get if you took propane and chlorinated it with chlorine and H-nu, the difference is much closer than it is in the bromination reaction on the left. There's much bigger difference between them. So that also helps favor the formation of the more highly substituted free radical. Okay, which then goes on to make your halogenated product. These are just the first step in the reactions. Okay? Okay, we also want to mention order of a reaction. You talked about this in general chemistry, and the order of a reaction lets you know what molecules are present in the rate determining step. So if you have some generic reaction, A plus B gives AB. That's pretty generic, okay? If you find that the rate is equal to some constant K, that's your rate constant, times a concentration of A, what that means is the reaction rate is only dependent on A. B is not involved, okay, in the reaction rate. So in other words, B is not involved in the rate determining step. We would say that the overall order of this reaction is 1. The reaction is also first order in A and 0 order in B. But we don't typically write the 0 order because anything to the 0 power is 1, remember. Okay, if your rate is equals some constant K times the concentration of A and the concentration of B, then this reaction rate is dependent on both A and B, and they are both present in the rate determining step. The order of this reaction overall is 2. We get that by adding the superscripts. Remember, if a superscript isn't written, it is 1. So 1 plus 1 is 2. Okay, we would also say that this reaction is first order in A and first order in B, but the overall order is 2, second order. Okay, what if you had a rate that's K times a concentration of A squared? Okay, the reaction rate is once again only dependent on the concentration of A, but there are 2 molecules of A in the rate determining step. The overall order of this reaction is again 2, like the previous example, but that's because 2 plus 0 is 2. Okay, so this is the end of chapter 4, and then I'm going to have to start another video to do chapter 5.
Bad problem.
It's not quit.
Where are you? What's there? Let's see. How do you make the help go away?
What's going on?